Okay, we're going to get started with this session. Thank you for joining us on Friday afternoon. We're going to talk about a roadmap for workflows as cyberinfrastructure for geosciences. And there's several really nice talks in this session. I hope you will enjoy them. Our first speaker had canceled a talk for a very important reason, I'm sure. But what I will do is get us started and give you an overview of workflows in general based on some discussions that we've been having as part of the conveners of the session. Let me start with that. So this work is something that appears in an article, the EOS transactions of the AGU. So you can find a lot more details there. I'll go a little bit quickly because of the time, but at least it will give you an idea of what workflows are and how they can be used. This work was done as part of the NSF EarthCube initiative. And I wanted to tell you a bit more about EarthCube, but I will do that in the third talk. For some reason, that got pushed to the third talk, so I will do that there. So what are workflows? Oftentimes, workflows for some decades now have been used to describe organizational processes. So, for example, you check into a hospital and you check in with a triage nurse and you go to the receptionist and you give them your insurance information. That's considered a workflow where there's a lot of different people, activities, and perhaps documents and actions that need to be coordinated. There's a different kind of workflow that you may have heard about, which are workflows of web services, which integrate business services from various sites, and that's also considered a workflow. In some sense, it pulls together a lot of different components. The kind of workflow that we're interested in is a kind of workflow that amalgamates computations. So these computational workflows really pull together a lot of different steps, a lot of different pieces of software that are needed to perform some pretty complex end-to-end computation. So I have an example here to do document classification where you might start doing a correlation score in the documents, then a feature selection, then create a model of that data, and then run this through a classifier on test data. So if these are steps that you follow to do certain amount of computations, that's a sketch of the workflow that you would follow. And what we do in workflow systems is actually capture these nominal sketches of computations into the actual steps that get executed in the computer, which an example is shown on the right-hand side. So you can see in green input data sets, and then in orange the different computational steps, and you may have parameters that are shown here also in orange because we can't see the difference very well here. Okay, and at the end there's some results that you want to look at. So why are workflows important? Because if you think about it, science is growing exponentially. We have a lot more data, we have a lot of network bandwidth, we have a lot of different computational capabilities, but actually there's always a human bottleneck in our ability to process and manage all of this information to create new science. And one of the things that is actually very time-consuming is to carry out all the computations that we often do manually, which is maybe prepare data, maybe integrate to different data sources, read the documentation, and so on. There's a lot of steps that get carried on manually. So workflows are a way to automate those processes, a way to help those processes be more efficient, a way to reuse those processes. They're really an item of science. There's really value to the creation of a new method or a new workflow. And also, they enable reproducibility. So if I have a computational artifact that actually represents how many computations were carried out, I can reproduce what someone else did more easily if I can get a hold of that computational artifact. So there's many benefits to capturing your computations as workflows. If you typically do these computations by going to the command line, loading something, then you open up Excel, then you save the result in some other file and so on and so forth. You have to do a lot of things manually that you don't have to do when you use workflows. So things that workflow systems can do are things like manage the execution of different steps for you. Even if they are parallel steps, they will know the dependencies between the jobs and when the different jobs need to be starting. They can also manage failure recovery. So if you find yourself actually a job failed in the middle of your computation, you have a complicated script that fired out that job, how do you recover from that failure? That's something that workflow systems can do for you. They can also move the data where you need to do the computations. They can farm computations to different resources. They can manage large data sets efficiently and reliably. They can do job submissions remotely, so you don't have to worry about, keeping track of that yourself. And also they'll record what you actually executed, so you don't have to wonder, how did I set that up? What was the parameter value that I used to get this particular result? So every resulting data set is annotated. There's lots of workflow systems out there. Some of them contain a lot of computational algorithms in them. For example, Galaxy or Gene Pattern contain a lot of biology and genomics kinds of algorithms. Others, like Lonely Pipeline, have biomedical image processing components in them. Others are more focused on libraries of workflows that you can share, like My Experiment, and others like Pegasus are focused on high-end computing. And there's a lot of different kinds of workflow systems. Each of them has a different use that I want to tell you about. So as a summary, workflows are a way to describe, compose, and execute groups of scientific computations that are related. When you think about a workflow, it describes the provenance of the results. So you can publish the workflow as a way to describe the provenance of the new data that you've created. You can use the workflow to discover how the data was produced and to also reproduce or reuse those computations. And there are actually many different opportunities to use workflows in geosciences. Some of them have already happened and others are potential opportunities that I want to talk about. So I'm going to give you examples of these use paradigms, but one of the things that we've been thinking about is that throughout the many different workflow systems and throughout many different kinds of projects and situations and environments in geosciences, there's actually lots of reasons and benefits to using workflows. So I'll go through each one of these 6 examples of potential use paradigms. And this is very useful when we talk to geoscientists in terms of potential collaborations and being able to exploit workflow technologies. So the first one is the center modeling paradigm. I'll use an example from the Iowa Flood Center. So in this kind of paradigm, a center actually does a lot of processing, perhaps regularly. In this case, actually using data collected from sensors. Their models are something that evolves over time. And every year they put out a lot of products that an entire community uses. And because their computations are repeated over time and improved over time, it's nice for them to be able to manage those computations appropriately. Also, it might be useful to tell the consumers of the data what were the steps that were followed to produce those results, so the provenance that I was describing. So this is an example, a center that actually runs a lot of computations regularly to serve a community with data products. Another kind of use case is what we call the long-tail paradigm. So this is an individual scientist that has to manage a lot of data, and workflows can help them do this more efficiently. And this is an example from a collaboration that my group had with UC Merced, where the scientists have a lot of local sensors. They take sensor data daily, and they would like to integrate this data with data from government sources and big data sources. And they actually have what you see in the middle is a nominal workflow where the data is integrated, prepared, and then different reaeration methods are selected depending on the flow of the water, and then the water metabolism is estimated. And what we do here is a workflow system that actually carries out these processes on a daily basis and automatically selects different models depending on the flow of the water. So the red line on the graph that you see on the top right is actually the system choosing different models daily to accommodate changes in flow. Without a workflow system, these individual scientists actually accumulate this data over time, and it takes a long time, many months, to generate the results. With this, they can see results on a daily basis. The high-end computing paradigm, this is a very clear use of workflows where you may have a lot of data. This is an example from EarthCube. There's others, many others, where you actually have a lot of data to manage, lots of computations. This is high-end computing kinds of needs, and actually workflow systems can really help you manage the scale, the reliability, and the efficiency for those computations. Another example is the whiteboard paradigm. This is an example from the Critical Zone Observatory, where you see on the lower left side that scientists often don't use a workflow system, but they actually draw out workflows and formulate workflows conceptually just to be able to understand how they exchange information and what different steps each of them is responsible for. So it's really the workflow as the whiteboard where the collaboration and the different pieces that everybody brings to the table is actually better understood and communicated. The metadata-rich paradigm is the kind of environment where, this is an example from EarthChem, where data is collected with and annotated with a lot of metadata. And as the data goes through computations, that metadata typically gets lost. And what you would like is an environment where, as computations are done on the data is incorporated into models or integrated with other data, all of the useful metadata is preserved. And that's also something that workflow systems are very good at. And finally, the software marketplace paradigm, where there's environments in geosciences where a lot of the same code, the same software is developed by many different groups, and it would be nice to be able to share that. So this is an example from RAPID. This is a hydrology modeling environment where they actually get data that they prepare and integrate from a number of national resources. And there's a lot of groups across the country that actually get data from the same resources. And there's a lot of investigators out there that will be downloading, preparing, integrating this kind of data to fit very similar kinds of models. And so it's useful to be able to share those data across different groups. And there's a notion of being able to post workflow fragments that others might be able to grab and reuse, not just individual codes. So this is my summary. I talked about 6 different kinds of uses of workflows, and you will be seeing examples of these throughout the presentations in the session. And I'm going to end here and put the schedule up, but I'm going to ask if anyone has questions or curiosities on the topics that I mentioned, or workflows in general. Questions? Go ahead, Mike.
You mentioned that the workflow itself serves as documentation of provenance. And what are your thoughts on what's needed around that for standardization of that information flow to really make that more than just sending your code, that's your provenance?
Okay, so Mike is asking that I mentioned that workflows serve as documentation of the provenance of the data, and your question was what can be done in terms of standardizing that exchange of how the information is flowing through different codes. So as of today, there's a W3C recommendation approved by the director on provenance, a provenance standard for the web. So this is the effort of 3 years trying to create a standard core ontology to represent provenance. So there's core concepts there such as activities, actors or agents, and then the products of the activities. And I think that fits workflows very well with some minor extensions. But it's a very good way to have a core standard for provenance.
So all of OPM has
Mm-hmm.
that?
Yes, so the open provenance model has been folded here. Other questions? Okay. I think I'm going to pass the floor to Carly Strasser, our next speaker, and let me help her set up.
If you just click, it goes forward. Okay. Do we need to restart this, dude? Okay. Great. Thank you. Thanks, Yolanda. So I think I'm in this session, not to say I don't want to be, but because I had the workflow, the word workflow in my title. But I'm actually going to talk more about the tool that we think of as fitting nicely into the workflow of the researcher, and that tool is called DataUp. So I'm from the California Digital Library, which is part of the University of California system, and we work with all 10 of the UC campuses to help facilitate digital archiving. So we just saw an example of all kinds of different workflow programs, and those are all meant to try and pull together the digital data alongside the complex workflows that all these researchers have been using. They jump around from program to program. I'm somebody who used to be a researcher, and so I'm very familiar with the idea of moving your data from Excel into MATLAB, maybe into R, creating your graphs for your papers. So this ends up causing a lot of problems, and so I like to say it makes a bit of a train wreck in terms of the way that researchers end up managing their data sets. And so it's a bit of a problem, and part of that is because this data management piece and being really careful about what you do with your data sets is kind of the foundation for being able to share your data with other people, and then of course being able to reuse those data sets in the future when you're not around anymore to tell people how you did your work. There are lots of hurdles to data stewardship. There's a lot of reasons that researchers don't do a very good job of managing data. The number one thing that comes out of their mouths if you ask is cost. So this has to do with mostly time, but also personnel and hardware and software costs. Those things all kind of mount up and it becomes a lower priority. There's a lot of confusion about metadata standards or data formats that they need to be using. There's a lot of differences in individual data sets, even things that are being collected or that are supposed to be fairly similar looking. When you actually pull up the spreadsheets, they can look extremely different. And that makes them difficult to integrate. And then lack of training. So there's not a lot of training at the graduate level or the undergraduate level for people to understand how to manage their data appropriately. There's a big fear of lost rights or benefits. There's a lot of folks that aren't interested in sharing their data because they're worried that they're going to get scooped or get proven wrong or get called out. And so we have a lot of sociocultural barriers associated with these data sharing questions. And then finally, no incentives, which is changing a little bit. But right now, the tenure and promotion process is not really rewarding people that manage their data sets well. It's focused on publication and not data publication, just regular publications. So how do we get to this kind of good data management, good data sharing, good data reuse situation? And the idea is to intercept researchers where they already work, and for better or for worse, that's in Microsoft Excel. So I talked to a lot of researchers at this conference last year, as well as a couple of others, and most of them use Excel at some point in their workflows. It's not often the end point, sometimes it's not the starting point, but it's usually there in the workflow somewhere. So the California Digital Library, where I work, got some funding from the Gordon and Betty Moore Foundation and partnered with Microsoft Research to create this DataUp tool. And the tagline is describe, manage, and share your data. But the idea behind the project was really to try and facilitate this archiving, sharing, and publishing of data sets. And so we kind of put our heads together to figure out how to do that, and we thought we should help with the data management and organization piece. And if we can do that piece, then that's really going to enable the data reuse and reproducibility of workflows in the future. So the DataUp tool is open source, and it was originally intended to serve Earth, ecological, environmental, atmospheric, oceanographic researchers. Those were the groups that the Gordon and Betty Moore Foundation is very interested in helping. However, the tool has kind of ended up being something that's useful no matter what, as long as you're using Excel. And it comes in two flavors, an add-in and a web application. And so just to give you a little bit more information about that. An add-in, if you're not familiar with them, it's a little piece of software. You download it, you install it on your computer. It appears as a ribbon in Microsoft Excel. However, with the caveat that it only works for Windows Excel 2007 and higher. So there are lots of scientists who are using older versions of Excel. There are lots of people who are Mac users, including myself. So the add-in wasn't a good solution for everybody. So we also developed a web-based application. And a web-based application is just a website that does something with the user's files. It has the advantage of working on any platform in any browser, but it's a new user interface. So there's a little bit of a trade-off there. People are very comfortable in Excel, but if we can get them into the web-based application, it opens up a little more opportunities in terms of the operating system. So the question of, what is DataUp actually going to do? We answered that by asking what the scientists need. So I went out and spoke to around 200 scientists, interviewing them at conferences as well as at the University of California at the 10 campuses. And the general conclusion is that there's no good data preservation going on. They're not really aware of any archives where they could put their data and tend to be fairly resistant to sharing. There's very poor data documentation, so lots of folks aren't writing down their metadata and aren't keeping track of what they're doing as they go through their analyses. And about 90% of the folks that I talked to use Excel in combination with other programs. So it was important that we make sure that we could facilitate Excel files, but also CSV files and other things that can be used in other programs. So the major features for DataUp, which are intended to, again, help scientists with this data sharing and data archiving, it helps the researcher perform a best practices check. It helps the researcher generate metadata. You can generate an identifier and therefore a data citation for the data set, and then eventually post that data set to a repository. So just to give you a couple of screenshots to show you what that looks like. This is the web app for DataUp, and you can see that along the bottom there are those kind of 5 basic steps, well, the 2 through 5 or the 1 through 4 from the previous slide. So you sign in to get started on this web app, and the first thing you do is you get a page where you can drag and drop or upload your data file in XLSX or CSV. And then once you click that post button on the right there, then you start going through these various steps. So the first is to check for best practices. There's 11 things it looks for, things like embedded comments or embedded figures or color-coded text or special characters. It tells you why it might be a problem. It gives you a way to fix that, and then it gives you the location in the spreadsheet of that potential error. When you generate the metadata, there's a little wizard that you can fill out. There's only 6 required elements, but there's 47 total that you can use to describe the data set. And it has things like temporal and geographic coverage, funders, who people should contact if they want to ask questions about the data set. Then the citation piece, you can retrieve an identifier from a repository by clicking that button on the right that's grayed out because I already clicked it. So there's an ARC identifier in that little window there, and that's a persistent identifier similar to a DOI, but slightly less regulated and free, unlike DOIs. And you can then generate that citation by clicking on the green button on the bottom there, and it actually creates something that you can copy and paste into your CV or give to the journal that wants you to publish your data. The final piece is to post, and so when you click post, it asks you to select a repository from the drop-down list, and there are currently 2. One is called OneShare, and the other is a practice repository. So if you want to play with DataUp, we have a practice repository that's kind of a sandbox where you can just kind of drop things in and see what happens. And once you accept that user agreement, then it's posted to the repository that you chose. And you get a little message that says that worked. So I'm going to talk a little more about OneShare in just a second, but I wanted to show you the 2 main differences with the add-in. So it does the exact same thing. Except you get a lovely ribbon at the top there that has those various steps that we just went through, the check for best practices, the metadata, the generating citation, and then posting to a repository. You can, however, actually see your data while you're going through these various steps. If you're using the add-in, that's not the case for the web app. And then the other major difference is that the metadata tab gets generated. So this does actually get generated in the web app. You just can't see it unless you download the file and open it in Excel. The metadata tab looks just like what you're seeing here, and it has all of those prompts that we saw in the wizard for creating metadata. And then on the right side is what I actually typed in when I was filling out my metadata. The nice thing is that you can now share this tab or the spreadsheet or save it as a CSV and give it to colleagues, and you can share the metadata actually and make sure that everybody's kind of doing the same thing. So where does the data go? Ideally, in the future, the data can go pretty much in any repository, anywhere. So this is the DataUp website, which is run out of Purdue, and they do a nice job of collating all the data repositories that are out there, so you can do searches for your subject or the name of the repository. They have 472 repositories listed in there, so it's just kind of a laundry list. So ideally, we'll have every repository, almost every repository in that drop-down list, but right now there's just one, and that's the OneShare repository, and the OneShare repository is actually a combination of the Merit repository, which is out of the California Digital Library, and DataOne. So if you don't know about DataOne, they had a booth at this meeting, but it's a big NSF project that's trying to federate all of the existing data repositories for Earth and atmospheric and environmental sciences. So you can go to a single website to the DataOne interface, do a search, and it's going to search over the metadata for all of the repositories that are members of DataOne. So OneShare is a special repository that we created along with some DataOne folks to basically house solely DataUp data. So if you put your data into a repository, right now it's going to automatically go into OneShare. And it's meant to be basically a data repository for anyone, anywhere. All you need to do is have an email address, and you can deposit data into OneShare. The one thing that potentially makes some people uncomfortable is that all data in OneShare is CC0 licensed and publicly available, so it's not intended for the sensitive data that you haven't published yet, but it's a really great spot to put data after you've already published it, and maybe you don't already have a relationship with the repository. You can use this as a place to have a home for your data. So the DataUp website looks like this. If you go to it, it's housed at the California Digital Library. And just to point out, if you click on the tab that says Start Using DataUp, it takes you to a page that gives you a little information. First of all, this is in beta. This is a kind of a 12-month development project with Microsoft Research. We no longer have developers devoted to the project, so it's beta. We don't have anyone who can fix any little bugs, but we are keeping track of those as they accumulate, and hopefully we'll be getting more funding in the next couple of months. Also, there's a little spot where you can read about which version of the tool you should use, so that walks you through the add-in versus the web app. And then you can actually go to the web application, which is the pages that I showed you earlier, or you can download the add-in, and you can do that right here from this page. And then this is the code site, so it is an open source project. The code's publicly available. It's on Bitbucket. That's also where the DataUp add-in lives. When you download it, it's from there. And then there's also documentation like installation guides. And let's see, if you go to the Wiki tab on the Bitbucket page, we have a nice laundry list of all the stuff that people have found that they want fixed, as well as these wonderful ideas that everybody has for DataUp. And they say, oh, well, you should really allow for other metadata standards, or you should really hook up with the citizen science eBird people. That's, we have a running list. We just need some developer money to do that. So the future of DataUp is basically three things, and that's to establish partnerships to engage developers and to build community. So we really need to pull together people who are interested in the project, but they need to be at the level of being able to either hire developers or be developers, because at this point we have lots of great ideas but no way to implement any of them. So the information about DataUp is on the top there. It does have the website, the Twitter feed, the Facebook page, and then the code, and then my information is down on the bottom there. So if y'all have any questions, I'm happy to answer them. Yes?
Did anyone at Microsoft encourage you to look at any of the Azure services for backup?
So the question was, Azure, were we encouraged to use Azure? So Azure is actually the cloud service that the entire web service lives on. So the both the add-in and the web app talk to a web service that's hosted on Azure. Yes?
If you submit data through DataUp, is there any way to make it discoverable? I mean, somebody got a bunch of faceless data files there. I mean, what good does that do?
Right.
And can people, is there some mechanism
To find the data.
search those or find it? I mean, do you have to know whose data is there? I mean,
Right.
how does that work? Or is this just the repository that you can cite? Is there a URL to
So, yeah, so right now there is a special collection on the Merit repository that you can go to and see what people have put into OneShare. However, the important thing is that it's all going to be harvested by Data One. So anybody who does searches with Data One is going to be able to find the OneShare data. So Data One already has things like the Dryad repository and Oak Ridge National Lab Stack repository, and they're in conversations with USGS and BCODemo and all kinds of other groups who are generating data. So anybody, I think Data One's only going to increase exponentially in its kind of use, in which case anything that goes in OneShare is going to be discoverable that way. Also, it has you get that persistent identifier, which goes to a URL. So if you have your data set and you give somebody that ARC identifier, they can find that data set very easily. Oh, there's a question in the back. 20 seconds, go.
So what's required for repositories
To be in the list? So all a repository needs to do is figure out the code and write up an API. We don't have any restrictions or requirements on who uses the code. It's open, it's out there, it's available. If they want to put their repository on the back end of DataUp, that's if they have developers to do it, then we very much encourage that. Data One has some loose standards that they keep for repositories that become part of the Data One network, but we're not making that distinction. Okay.
Thank you.
Thanks.
Thank you very much. For some reason, I'm not able to set this up. I don't know what I'm doing wrong. Okay, I'll just count it backwards. Okay, so the next talk is an overview of a roadmap for workflows in geosciences that was part of the EarthCube effort from NSF. I'm going to start describing a little bit of background about EarthCube and then walk you through this roadmap on workflows. So there's been several sessions at AGU on EarthCube, and I hope that some of you have attended them. There's a lot of activities and a lot of energy in the community about it. It's an initiative to look at how can we improve cyber infrastructure for geosciences, and it's a very community-driven kind of framework. There's a website that's kind of a social side. There's a URL there at the bottom on the right. There's more than 1,000 people participating and contributing to it. There's a lot of discussions going on. The outcomes or the expected outcomes of this multi-year and very ambitious project is to transform practices within geosciences in the next decade, unprecedented new capabilities to researchers, and what I think is very important, vastly improve the productivity of the community. How can we make the community, and that is including everybody in the community, from someone sitting on their desk in a smaller university or collecting samples from a lake to those that are sitting in supercomputing centers. How can we improve the productivity of the community, accelerate research in the community, and also provide a knowledge management framework for geosciences. And I think that this is where workflows have a large role to play as first-class citizens of science. There's a value to an end-to-end data processing method that is captured in workflows. So what I'm showing now on the right-hand side are 4 groups that NSF decided to form based on several months of initial discussions with the community and several meetings where various topics were brought up. One is data, another one is workflows, a third one is semantics, and a fourth one was governance. So the focus of this session really in this talk is on the workflow side. There's a website at the top. It's a Google site where you can find a lot of details about all the activities that led to this roadmap being published. I also included the pointer to the EarthCube website. You can just search for it and you'll run across it. There's a lot of information in this website because we try to be as transparent as possible about it. Why was it important to create a community group around workflows? Why did we want to understand the role of workflows in the future of geosciences? There were a lot of different people and different discussions that led to highlight that it's important to find methods, data analysis methods that people are using. We call that workflow discovery. Also, keeping metadata about new data products that are generated through computations and the provenance of those data products, it was also important, and that's something that we often do through workflows. Also workflow execution management. As our data sizes grow and the data becomes more heterogeneous, it's important to be able to manage better the execution. And finally, to be able to do data management within workflows. So a lot of the times we integrate computations with integration, with visualization, and many different steps that are useful to manage through some integrated framework. So this workflow group was created. I'm naming here the people in the steering committee, and the important thing is that it was formed by both geoscientists and computer scientists. So I think that that's a nice combination so that we're not just developing technology, but we actually let it be driven by what scientists actually need. So the outline of this roadmap, and if you go through the different sections in the website, followed a structure that NSF requested from us. So there's 10 different sections, so I'm going to go in the rest of the talk throughout these sections. And what I wanted to highlight is that perhaps one way to look at this roadmap is that it's recommending to establish a steering committee that coordinates activities of several task forces. And these task forces have different functions to play in terms of interacting with the community or serving the community in different ways. Of course, the task forces would be formed by people from the community, but they would have some charter to make decisions and to understand and produce a consensus on various aspects of the workflows roadmap activities. Okay, so some of the initial work that we did to create the roadmap actually has to do with a lot of these task forces. So, for example, we created a website. We have a final report of this roadmap. We had an EOS letter article that I presented earlier in the section. All of these things are ways to communicate with the community, and that can grow as a community task force, communications task force. We also saw a need to have a way to collect how workflows are being used today, what are future requirements. So we actually created a workflow primer so that people understand what workflows are and where the opportunities are for everyone to use workflows and the benefits from that. There was also in the roadmap an engagement task force which would help engage the community, and we're doing that through defining use paradigms that I talked about earlier in the session, but also we're collecting workflow vignettes. These are very small, brief use cases that actually illustrate either a current use of workflows or a potential opportunity for benefits of workflows. And we're still collecting those. If any of you has any to contribute, please contact us. A prototyping task force would be more devoted towards developing prototypes that could be good demonstrations of benefits of workflows. And that's something that we didn't do as part of these activities. Another task force would be on assessment, really understanding whether the EarthCube activities are really making a change in the community at large. And as part of this, we developed a workflow questionnaire with a detailed breakdown of different ways to assess whether workflows are having an impact. And finally, a community interaction task force. So these are things like, can we coordinate workflows for geospatial kinds of data management with activities within OGC? Or can we coordinate workflows in geosciences with the W3C provenance standard that we just discussed? So as part of this, we had a lot of virtual meetings with a lot of invited participants from different communities, existing projects, standard bodies, all kinds of different groups, as well as face-to-face workshops. So this is the essence of the roadmap, to create these task forces that can make connections with the community, help us reach consensus, and assess if workflows are making a difference. So as part of the roadmap, the purpose of having really a workflows community group alive during the duration of EarthCube is to identify challenges and help the community solve them and address them together. By having a standing group, we can do that better. This includes education, both to computer scientists and geoscientists. Also, being able to enable better collaborations in terms of workflow software development, and understand what are the grand challenges that we need to go and do basic computer science research on to serve geosciences. So these are central to the roadmap, and we don't see the roadmap as something that we created and is done, but as something that would be alive through the life of workflows community group in EarthCube. One of the sections in the roadmap was to discuss communication. How is the communication going to occur in terms of a discourse in geosciences regarding workflows? So there's a lot of geoscience researchers that are not aware of workflow technologies, but there's also a lot of current uses of workflows in geosciences that workflow researchers like myself don't know about. And we've actually uncovered many such cases throughout our conversations in the last few months. So we see the communications task force as a way to address this and helping in both directions. And as I mentioned, we've so far created some documents and mechanisms to facilitate this conversation. But this is very important to understand both sides. In terms of challenges, there's a number of technical challenges, and as a computer scientist, I could stand here all day and tell you about many of these. But some of the more interesting ones might be that the complexity of the data sets and the computations needed in geosciences are increasingly challenging for us each year. So geoscientists keep our life very interesting. Also, the scientific processes are more and more collaborative. So a lot of these workflows are designed or run or looked at by many. And so we need to be able to enable that kind of collaborative creation of workflows. And a third challenge that I'll highlight is that there's a lot of workflow systems available. And so that creates a challenge also, because today as a scientist, I need a workflow system that's very flexible and fluid, and I can prototype things very quickly. But 3 years from now, I want that workflow to run in high-end computers at a high throughput kind of data. And I may need a different kind of workflow infrastructure. So that creates challenges for all of us to enable those kinds of things. So I think that the next point talks more about the communication needed between the computer science and the geoscience community in terms of being able to communicate that different workflow systems are better or designed for different tasks, and being able to match up needs with capabilities is an important piece. We thought that reproducibility is a big challenge. So in science in general, so we see a lot of articles on retractions of publications because the results could not be reproduced. There was an article in the Wall Street Journal in December last year about pharmaceutical companies spending millions trying to reproduce published results in the literature and being unable to do so. So there's a lot of issues in terms of reproducing science results. And I think one of our challenges is to make sure that workflows can play a role in those needs. And then, of course, there's a lot of evolving technologies and infrastructures where workflows run, and the general environment of science. So if we want to make workflows that we can reuse or replicate in 10 years or produce in 10 years, that's a bit challenging. So that's a summary of the challenges. In terms of requirements, we really thought that it would be very useful to create a task force that would be devoted just to this. We have out a workflows community questionnaire to start to do that, and we got excellent responses with very many good points. And the questionnaire is still open to anyone willing to give us additional input. I mentioned the prototyping task force, but this would be, selected high payoff investments in prototyping workflow applications that could give this technology good visibility in geosciences. Status refers more to how can we understand the current status, who is using workflows and so on. And I'll point you to the website to see more details on this. In terms of solutions, how do we match groups that may need workflow technologies with solutions? And so for this, I'll highlight that we've been collecting workflow vignettes. So these are small use cases that highlight whether someone's using workflows and what benefits are getting from them, or a group that might benefit from workflows, and they'll acknowledge that, but they don't have the resources or the right collaborations in place to make it happen. So these workflow vignettes are growing, and that's also something that we continue to collect. In terms of the process, this was referring towards how do we engage the community. So standards bodies or already existing projects. Some projects are funded projects, established collaborations, multi-years that are quite complex. So we had a task force designed to do that. In terms of the timeline, we thought that there should be activities going on throughout the duration, the next few years, but there should be an awareness thrust that's really gathering information and keeping us informed about how the community is reacting, how workflows are making an impact, and so on and so forth. The enabling thrust would be more focused on prototyping, pursuing good opportunities for collaboration or for dissemination, and so on. And then a third thrust on infrastructure and services. So can we, for example, offer central ways to give you a unique identifier for your workflow, a DOI for your workflow, for example, as a service to geosciences. And I already mentioned the different task forces and the steering committee within the workflows group, but we also thought it would be useful to have a central location for personnel that scientists can come and visit and talk and engage, and have someone that responds and really engages on it. And then there was a final section on potential risk that I'm going to skip. So this is just an overview of the roadmap. And as I mentioned, several task forces that we've already started to germinate with documents and activities. And then we also had a good timeline, I think, for activities, starting with engaging the community, and then a second phase with more prototyping, and then a third phase with support and infrastructure to the community. Okay, so I'm going to take questions. If someone has questions about EarthCube, we have Barbara Ransom from NSF here ready to answer. Or if you have questions about the workflow roadmap, there's a number of us that participated that are here. One question? The final product of a workflow group? So I think what we tried to do is a roadmap towards that describes how the activities of the group would be coordinated. And I don't think that today we have a good picture of some particular final product. I think that we have a good picture that the community would be more productive. Along the EarthCube goals that we talked about, the community would be more productive, that there would be better support for knowledge management in terms of these workflows and these processes. So we have a lot of ideas about, end goals, but I think the way to get there has to be very community driven. Barbara?
I see you have a workflows
So the reason for a workflow synthesis center is that if you have a lot of task forces just, talking and meeting and writing reports and coming up with ideas, you also need to be able to, a scientist that really wants to use workflows in their center, for example, and adopt that. What's their first step? What do? They're going to need to engage someone to follow up and to actually describe to them, point them in the right direction, work with them to adopt this technology. So just to jumpstart activities in engaging computer scientists and geoscientists. So the idea was to be able to have people in place that are available and are supported to engage scientists to do this. Okay, I'm going to move on to the next talk. Thank you. Marlon.
Okay. All right. Thanks everybody for coming to this very late session. So, how do I advance the slide? Okay, just click the mouse. Okay. All right, great. Thank you. All right, so I'm going to talk about building scientific workflows for geosciences with open community software. So, the real topic here is this last bit about open community software. So to give you a little bit of background about our group back at Indiana University and some of our collaborators and the environment we work on, we do a lot of what Yolanda called the high-performance computing workflow paradigm. We work with the XSEED project, which is a big NSF-funded project to provide supercomputing and other high-performance computing resources to academic investigators in the U.S. And so it is an amalgamation of lots of resources from lots of different universities. XSEED doesn't actually pay for the computers anymore. That was the predecessor TeraGrid did some of that. But what they do is provide uniform administrative layer, and also they're working on extending the TeraGrid middleware layer to make all these things look more, be more accessible as a programming is a distributed programming environment where I can easily get data in and out of different centers, launch and manage applications in a similar way on the different centers and so forth, and do all this remotely and securely through grid middleware services. So, oops, backwards. This is not good. We have some excitement. All right, so. Generally what our group does, stepping a little bit higher level from scientific workflows, is we work with scientific workflows to support science gateways. So this is basically, these are higher level environments for helping scientists who have really challenging and interesting problems that you want to spread across multiple resources, or also you're on the other end of the spectrum, you're actually looking for providing a web-based resource for making it really easy for a large community of users to access applications and data sets and so forth that are available on XSEED. So separate to this, we have, so part of the focus here in our talk is the EarthCube effort, but also we have ScienceGateways.org is a effort that is related to, this is an attempt to build or prototype an institute that would be larger than, or not just concentrating on XSEED resources, but also support gateways for campus resources, for other types of grids, for other infrastructure, for cloud resources, so forth. If you're interested, we can go to the website, or I have a little handout, a little postcard I'll be happy to give you. All right, so workflows are, for us, a subset of science gateways. One of our driving use cases here, this is actually a historical use case because the project has ended. Many of you might have heard of the LEAD project from a few years ago. It's Linked Environments for Atmospheric Discovery, and so this was one of their driving use cases that they built out. So you have streaming observations coming in for, in this case, weather data, which you're going to do data mining on, and you're searching for evidence that storms are forming. When storms form, you're going to run a mesoscale weather forecasting code called WRF. Preferably, you're going to do this to support real-time weather forecasting on, and so this is a code that's going to be actually running on Exceed, or actually, because this is a historical code, this would run on TeraGrid. And you want to use this as a workflow for helping investigators model storms as they're actually occurring. So this was built out using some software that was based on service-oriented architecture principles. We have a project from the NSF called the Open Gateway Computing Environments Project, where we worked really hard to generalize this software and apply it to other domains, throw away a lot of stuff that was really, a good student research project, but, wasn't really key to the core operations of what we wanted to do. And so we've taken this software and have applied it to a number of additional projects. One of which I picked not because I know a lot about it, but because it's one of the advanced support activities we work with in collaboration with the University of Alabama, Huntsville, on Exceed resources. So this is for us a workflow, and a high-performance computing style of workflow. So the top center is if you've seen such things before, this is a workflow composition tool. It's, in our case, a Java Web Start application run on your desktop. So what you want to do is combine a number of independently developed, sometimes third-party applications into a composite graph that you want to have executed. So the big yellow, faded yellow boxes there, each of those is a separate application that's going to be running on some Exceed resource, and then the other steps there are the bluer shaded boxes, if my color vision is working correctly, are going to be input files. So if you follow the connections through there, you actually see, of course, this is if you remember your computer science classes, this is a directed acyclic graph. There are many variations and complications on these types of workflows. But for us, this is a classic problem. I have input data. I need to perform some image analysis routines on. I need to then apply a separate classification algorithm on, and so forth, and so I get the final result. So the collaborators provide the science, and we provide the tools for hooking these things together. Okay, so the software that we use in our group to support these different projects is called Apache Airavata. Say a little bit more about the Apache part of it in a minute, but so to give you an idea of how this stuff kind of works under the hood, and I don't have a huge amount of time to go through all these things, but on the left-hand side you have the end user who will compose a workflow and distribute it or contribute it into a workflow registry. The registry, in our case, is a fairly simple activity for right now. For historical reasons, it's used primarily to store and fetch descriptions of resources of the little components that you want to make into your workflow, the different applications, the host machines that are available to you, things like that, and then also the composed workflows themselves and their instances after you execute them. So typically you'll have one person who is responsible, or a small number of people who are responsible for actually composing the workflows, because it can be a trial and error process, and there's more than just hooking things together. There's a science that has to be behind the actual workflow that you want to execute. But after you like it, you publish it, you can make it available to others to actually execute. So those are then retrieved from the registry, and as a template, specific input values are provided. So if I'm running, say, the UAH or the Dust Over Africa problem, I'll provide it, for example, an input region of interest. So after the inputs are provided, the actual execution is handed off to a web service called the Workflow Interpreter, which will push through the graph that you've created or the more complicated construction that you have created. Each node in that graph is, again, primarily for us, these are wrapped applications running on Exceed, and so these are things that are going to be individually wrapped as secure web services through an application factory. So the last component is the API component, which is the entrance, the blue box on the with the arrow, the Apache feather in the middle. So each of those components, the message box, the interpreter, the registry, the application factories, these are all web services. They all have programming interfaces, but it's not necessarily something that is easy to program against. And also we have tendencies to change things when we need to make an improvement. So the API is not just a shallow thing, but it's actually our efforts to make to be the one stop that you go to when you're going to be programming against all the services underneath in that larger blue box. So this is the one place where you go to get access to the registry, the interpreter, to get communications about state changes in your workflow, things like that. So this is AGU, and here's a bunch of non-G stuff. But so I just wanted to give you an idea that we work on lots of different scientific domains that have these types of workflow problems. This is really a generalizable thing. This is not just something that geophysicists or people in the geo world or atmospheric world or so forth need to have specialized tools for. And I'm not going to say anything more about these, except if you're really interested, we have papers about each one of these. So now for the real, at the 11-minute mark, now for the real topic. What do we see for? What do I personally see, and what does Suresh and other people in our group back in Indiana see as a problem for EarthCube and other efforts like this? And one question we have a lot of is, how open is your Cyberinfrastructure software? So a lot of work has been done on open source licensing, encouraging open source licensing within the NSF. There's been a lot of work on open standards. Maybe you've been putting your code in the right places so people can go and look at it. But I think the open that's missing, and maybe there are others, but the open that we see as missing in this checklist is open governance. So what do I mean by that? Well, what we're exploring in our group, and we might hear a little bit later from another speaker, is we're looking at how to build open community software, not just open source software. So why do you need this? Well, for one thing, we think you need it for sustainability. So if you're going to have a sustainable project, which doesn't necessarily depend upon you, one group at one place being funded all the time to work on this software, but if you think it really is useful and deserves a life that can withstand the vagaries of federal funding, then you should figure out how to get as many people as possible interested in and contributing to and working on your software. And so if you're going to do that, if you're going to have, that's the path, I think, to sustainability. If you're going to do that, then you're going to have to figure out how to give incentives for people to participate in your project. And if you're going to do that, if you're going to manage such a thing, you're going to have to know how to govern it. And so you can figure this out by yourself by trial and error. We chose to join the Apache Software Foundation. We thought it was appropriate for our project. And Apache gives us a model for doing things like, how do you do software releases? How do you know when you're ready? Is the code ready for release? How do you handle contributions from people who show up and say, hey, I saw your nice they're open source software, and I figured out that you have a bug here, or I've added this nice feature. What do you do? And once you get people doing this, how do you give them, how do you give credit in a neutral way across when you have developers from many different places working together. How do you determine that somebody should be actually added to the project as a full-fledged member with voting rights and all these sorts of things about making decisions about the directions that the project should go? And also, if you're a large project, you might have a team of lawyers to help you, but if you're a small project, sustainability has to scale down, not just up. And so how do you handle, or how can you get some help with intellectual property and legal issues? So our concern here is that there's been a lot of work of people who are still arguing about the bricks and the foundation, and that's not what we'd like to see. What we'd like to see is that people learn how to collaborate on the foundational pieces. So Yolanda outlined several different paradigms for different workflows. So you can think maybe each one of these as a foundation. And let's figure out how to work together on those pieces and then compete on the more interesting research topics. So where we have groups from different organizations all working together on, say, the same reference implementation of an open standard, but then the cool parts are all, if you're in the academic world and you want to do research, the cool parts are all at the top. So how can you do this? And this is what we're working on in Apache. So I'm out of time. Thanks very much. Overtime, actually. But you can find out more information. Please feel free to contact me. Thank you.
You want to take one question while you set up?
Yeah, I'll take one question if anybody's so inclined. Yes.
How would you see this working into Yolanda's recommendation of having some kind of a workflow synthesis center? Is this like something completely different? How would these two, is there any relationship between those two, or could there be?
Possibly. So I think the synthesis center would be working on, let's say, I have points of contact between different paradigms, different workflow types, and so part of this is going to be working out how how the standards of interfaces are operating, or points of contact between those different types of workflow paradigms. So while you're working all that out, what I hate to see is everybody run off, and now we're going to have our own separate implementations of this thing, and because there are standards, we're all going to magically work together. What I'd rather see is that we have a way of collaborating collectively on those glue pieces, if we can. So if it's really, anyway, so if it's really these are, I'm thinking off the top of my head here to this question. I think that's really what I'd like to see is less people in cyber infrastructure thinking themselves as vendors of software, and more of them thinking as collaborators on common pieces of software. And so those little pieces would be, I think, good candidates for going through, some open governance process.
Thank you. The next talk is an invited talk by Scott Peckham on modeling frameworks.
Thank you. Just the arrow keys? Do they work for the... Will those
You
work
can
too?
just click and that goes forward.
Okay. So I'd like to thank the conveners for inviting me. I really appreciate it. And thank all of you for hanging in there till the bitter end. We're on the tail end of Friday. So what I'm going to do today is talk about some of the overlap between the things that we do in the modeling frameworks as a class of software and what happens in workflows, and some of the big issues that we've been facing over the last 5 years at CSDMS. And this is going to be sort of a high level introducing the key concepts that you think about when you're trying to architect these types of things. So this first slide just lists some of the big issues or key problems. We have a lot of heterogeneity. As you can see from any of the talks here, there's lots of resources out there, data models, web services, but they're all different. And the questions are, how do you accommodate those differences? And the differences for us, for example, could be names of variables, data types, units, different computational grids, time steps. And then there's questions like, how do you find a resource if it's out on the web somewhere, or even if it's on your same computer? How do you find a provider for the variable that you need? And there's linking and connecting issues, and those could be sort of tight coupling or loose coupling issues, because if you're connecting to something across the web, that's one thing, but if you're connecting to a pointer to a variable on a machine, that's different, and there's different data transfer rates that are really important for that. And so you can't think of all of these problems being solved by web services, because a lot of the high performance stuff has to happen on the same machine in order to be fast enough to get the results that they try to get. In some of those systems, the speed of light along a wire is the limiting performance bottleneck. And so then there's a whole set of semantic issues, and from my point of view, that's one of the biggest, hardest problems that we have, because there's not really a single solution that's domain independent that allows that to be easily cracked the way some of these other things have been done. And then there's performance, speed, and efficiency issues. And I think EarthCube was kicked off by talking about the 80-20 problem, which is a lot of researchers complain about spending 80% of the time getting the data together, doing the patching, mosaicing, grunt work type stuff, and then only 20% doing actual science. And we'd like to really reverse that, but it takes a lot of automation and seamless integration to make that happen. So a couple of key terms before I get into the slides that have graphics, so hang in there. First of all, when we're talking at CSDMS, we deal with a lot of models. We have models from across the geosciences, not just in one domain. And so we've come to see at least one definition of a model that's very broad as some kind of a piece of software that has a bunch of state variables discretized in space on some kind of a computational grid, and new values are computed from old values by marching forward in time using some kind of rules. And if you have some kind of a model that just produces static data, it doesn't change in time, that's kind of a degenerate case. But this is the pattern that a large majority of our models we run into look like. There are some that don't fit this, like if you try to have molecular models, they don't live on a grid, and so that's different. But then a model component is when you specially prepare that model for some plug-and-play reusability, because you'd like to reuse it in more general contexts. And that means wrapping it with some kind of a standard interface, which I'll talk about more, and compiling it for language interoperability so that you can make calls from a piece of code that was written in one language to a piece written in another language without translating anything, without translating to a common language. And then interfaces is another, just a big term to understand from a computer science point of view. It's not like a graphical interface, but it's that a standardized set of functions that callers use to interact with the resource. And that resource could be a web service, or it could be a database, or it could be a model. But since everybody has their own, as long as everybody has their own functions for that, it's really hard to learn lots and lots of interfaces for getting a job done. It's nice if you have one standard interface that you can work with and code to. Now, the last two things I have in yellow there should be thought of as sort of classes of software. There's modeling framework software, of which there's many types. There's CSDMS, the one we work on. There's OpenMI, there's ESMF, there's OMS. There's a number of those, just like there's a number of workflow system softwares like Pegasus and Kepler and Cyberinfrastructure and so forth. But each of those classes of software address certain sets of problems in a fairly similar way. So a modeling framework is really a software container where precompiled model components are instantiated, so they're generally treated as objects and instances of a class, and they're configured, dynamically linked, and then someone creates a custom model. And the framework, you can sort of think of it being able to look down into the innards of all the models that it's instantiated and query them and get information from them sort of with a bird's eye view. And so that puts the framework in a unique position to pair up users and providers and to do other sorts of mediation things. And then the workflows, and as I understand them, and I don't know if I can give as good of a definition for them, but they're a little different, and they're similar, but they're a little different in the sense that it tends to be a chain of steps where you've got a complete product after each step that goes on to some other step which may involve a different application. And the data, the products that are passed from one to the next are passed as files, which involves reading and writing to a disk as opposed to looking at references. And so there's a different time scale involved in terms of some of the stuff we do could not be implemented in this way, but one of our models that we build could be one node in a workflow that involves getting data, running our composite model, and then going on doing post-processing. So this is another way to sort of visualize what happens with interfaces. Is the top is the way your resources look before you've done anything to standardize them. And each one is unique. They have their own way of doing things. They respond differently, can get out of control. And then after you've put a common interface on them, the analogy of a person wearing a uniform and responding to commands like halt and march and those kind of things is a really good analogy, because that's kind of what we're doing. Is there's still an individual inside of that uniform, but now he's been made to be standardized and to respond to in standard ways to standard things. And it's easier to interchange units, and to have a chain of command is very important. They understand in any situation who's in charge. And that's the kind of things we need in the case of modeling environments as well. Now, I was in the EarthCube talks, this idea of making bridges between silos kept coming up. So I was looking on the web for some silo pictures, and it turns out they have bridges on top of them. So it was easy to find a nice picture for that. They're not really, they're kind of bridges. They're little catwalks, I think. But those silos represent, they could be domains like hydrology and meteorology. They could be federal agencies like NASA and NOAA, or whatever they are. But they have their own internal practices and their own, what I would call local standards that they are used to using, that they use. And then when they want to share across with some other silo, they need to come up with some global standard that they both agree on. And that's where things, we want to have a democratic sort of a situation where you're free to do what you want in your own silo, but you're not free to do what you want when it comes time to actually coordinate things. We can't allow that at that stage. So there has to be some kind of a bridge thing at that point. Now, this plot's meant to illustrate how standards reduce complexity, and you think of those dots around the outside of that circle as a bunch of things. Like in one case, they could be computer languages, or they could be human languages, or they could be some kind of resources you need to link. But if you were going to take the approach, the way things usually start is they do pairwise reconciliations between these various things, and that rapidly gets out of hand. That grows as n squared, and you see all the line connections between everything and everything else. And that's a lot of complexity, and it's not sustainable, it's not efficient. The alternative, which you see over and over and over again in these architectures, is a hub and spoke sort of a design somewhere at the back. And you actually introduce something new. You introduce a new thing and put it as the hub, which is sort of a standard representation for the general thing. So it's agnostic to all the ones on the outside, but it's able to describe them all in a common way. And then when you want to go from one to the other, you go to the hub first and then out again. And that's a lot more manageable, and it grows as the costs and the problems grow as n instead of n squared. Now, another really important issue with this I already kind of alluded to is data transfer rates, and whether you need to connect across a network, or whether you're going to read from a file, do file I/O to connect two models, or whether you're going to connect them by having them look at the same references and pointers in memory. And there's orders of magnitude differences between some of those things. And so it's a key design issue. And one of there's a talk online by one of the Google executives that has similar sort of a plot like this of speed, different relative speeds. And he said it's things everyone should know. That was the title of his slide when he had one like this. Because if you're trying to do back-of-the-envelope calculations to figure out how well a certain approach is going to work, or whether you can deploy something as a web service and so forth, you need to think about these speeds and how much data is going to actually be moving back and forth, and what the costs are going to be. Now, I'm going to talk a little bit about modeling frameworks in particular. And like I said before, the modeling frameworks really help you take a lot of reusable bits of model code, make a new model, custom model, and then that could now be a node in a workflow, because those models always need input data, and it's always a hassle to get the input data prepared for the model. And so a workflow is ideal for getting all those preparatory steps, which tend to be linear, in place, and then having the files sitting there that the models want to read in to work on. But then as the models run, they share the data that they are advancing in time among themselves by references. So if you ask, well, for models, what's the ways they can differ, there's sort of 5 key ways that they differ that we have to have solutions for. There's the programming language they're written in. There's the computational grid, which could be triangles or rectangles or some other kind of polygons or cells. There's time-stepping schemes that are fixed time steps, or they adapt in time and change, or other types. There's variable names that one programmer calls something and another programmer calls it something else, and how do you know it's the same variable? And there's different units, which if you don't convert for them, then you're going to have problems there. And so luckily there's solutions to most of these things already, except like I said before, the semantic mediation, the standard names thing, having a hub that you can map to, referring back to that hub and spoke diagram, for standard names would be extremely useful. And it's not really in place yet. So we've been working on that, and I'll talk a little bit more about that in a minute. For the language interoperability, there's a great tool that DOE developed over many years, over a decade or more, that we use, and it works great. And it does use this hub and spoke approach. It actually represents the interfaces to the various things you're trying to couple in a form called Cidal, which is independent of the things outside, and everything maps to and from that, and it's very efficient. We've introduced something in order to get the models that are contributed to us interoperable as easily as possible. We've introduced something called the Basic Model Interface Standard, and there's a lot of design criteria on this in terms of making it an easy target for developers to hit, and something they'll actually try to hit that they feel that it's not going to be too daunting to hit. And when it comes down to the framework, which is looking down on these model bits, trying to reconcile the differences between their different grids or the different variable names, it needs to be able to query those models about their differences, and it needs to be able to control them as if it has a remote control, a universal remote, and it needs to get and set variables and so forth. And so we've come up with a way to do that, which is described on our website. And so this is kind of what it sounds like when CSDMS is talking to a model, kind of a conversation. It says, so tell me about yourself. The model says, I need input variables A, B, and C. I provide output variables X, Y, Z. I use adaptive time stepping. I use this type of grid. I like pina coladas and getting caught in the rain. Those are great attributes. I think we can hook you up. Am I just an object to you? Yes. Your state variables are your data members, and your member functions consist of the BMI functions. I won't get into this too much, but we've cleanly separated with BMI all the stuff that has to happen up in the framework that is very technical from what the developer needs to see and think about. And that's so the developers hit the BMI target, and then a wrapper slips on top of their code and automatically provides them with the ability to talk to other components. Now, the standard names is something that I mentioned that we had to really think about. And we've got some prototypes, and it's a work in progress, but I'll put a link on the very last slide that tells more about this. The basic idea is to construct these names with an object part, possible operation name like a derivative, an integral, or a max or min or something like that, and then a quantity name, which could be like a velocity or pressure or something in particular. And then there's ways to chain together adjectives to be sure you're talking about the right type of connectivity or the right type of velocity. There's ways to chain together objects because you're starting from a broad outside object like the atmosphere and then drilling down to the parts inside, to the objects inside of that, like the carbon dioxide or something. And so we've thought through, by looking at lots and lots and lots of examples, we've thought through how to organize this in a nice way, and we're starting to interact with people on that problem. This is just showing when you're trying to model, you often want to be able to swap out different ways of doing the same thing, some very simple, some very complicated. Like for snow melt, you can use temperature to melt the snow as a first cut solution, but a full energy balance does a lot better job. And so in a framework, one of the things we do is we want to swap out different simple and easy ways of doing that. And we've got a modeling tool we've developed which makes that possible, where you choose from this palette on the left from multiple options for a given process, drop them into the interior, click on a button to see a dialog and configure them, and then the framework auto-connects them, and you have a model in minutes that you just created from these plug-and-play pieces. And so that's it. This is there's a paper we have that came out in Computers and Geosciences, available online, and we have an extensive wiki website that has all kinds of resources, including the BMI description and the standard names stuff. Thank you. I guess I have time for at least one question, if there is one. See, way over in the back. Yeah, we studied the 2,134 CF convention standard names, looking for patterns and looking for things. And there were things about that were good, but there was other things that didn't extend across domains. It was very domain specific to the ocean atmosphere community. And one of the things we didn't like is they put assumptions in the names. And we put those outside into a separate XML file so that you can have a lot more assumptions listed for a given variable. And we talk about those differences on our website, so you can go there and see more. Thank you.
Oh, I know. So it's red. Somebody tell me when it's 15. Okay, hi, I'm Tom Painter, and I'm collaborating with Chris Mattman, Mary Jo Brodzik, Annie Bryant, Cam Goodale, Andrew Hart, Paul Ramirez, Carl Rittger, Felix Seidel, and Paul Zimdars. This is the Snow Data System Group from the Jet Propulsion Laboratory, and also from the National Snow and Ice Data Center. And I'm talking largely about the activities that we have been doing in the last couple of years since the February morning when I woke up and freaked out and yelled an expletive and then made a phone call. So I want to start with the mountain snowpack, which is my focus. I'm a physical scientist, and the mountain snowpack is highly, highly variable. It's variable due to topography. It's variable due to meteorology. It's variable due to, in this case, deposition of dust. In this case, in the Tian Shan in Kazakhstan. And then it's a strong controller of glacier dynamics. And much of what controls that comes from the variation in albedo. Let me see if I can. There we go. Okay, so albedo is the total reflectivity of a surface, but that can also be considered spectrally, and that is what we've been doing from a data standpoint, is considering it more and more spectrally. So what controls snowmelt? Well, I won't drag you through this since it's 5:40 on Friday, and my wife is hungry. But absorbed sunlight is the dominant control on snowmelt, despite what you hear about temperature increases. Temperature increases affect the phase of precipitation, okay, and that's what really has its big impact. So whether precipitation falls as rain or snow, that's where temperature comes into play. But once the snow is deposited, then the big control comes from the absorbed sunlight, and if you change that, say, with warming, which increases snow grain size, or with dust or black carbon, then you increase the snowmelt, and that impacts the water resources. It also impacts the glaciology. So I actually meant to put in a slide here that showed that our first remote sensing retrieval from the Tyros-1 satellite in 1960, the first parameter that we retrieved from that was snow cover in Newfoundland and Nova Scotia. It was a very easy mapping because it was nicely discriminated against the ocean. And there was not a huge amount of data involved with that. We've made this transition, though. So about 12 years ago, we launched the first MODIS instrument on the EOS Terra, and that saw a big jump, getting us 7 surface reflectance bands across the solar reflected spectrum. That was a big jump from the 2 bands that we had from the advanced very high resolution radiometer. And these 7 among 36 other bands in the MODIS spectrum. But we can leverage that information now to understand more and more about the snowpack. So we do that through my model, the MODSCAG, MODIS Snow Covered Area and Grain Size, which is a spectral mixture analysis, essentially a linear algebra inversion for the percent cover of snow per pixel, and what in that fractional cover, what the snow grain size is, and by extension then what the snow albedo is in that fractional cover. So we're going to more and more detailed retrievals. Those retrievals look like this. So this is the Sierra Nevada. This is just a color composite. This is the fractional snow cover retrieval and the snow grain size per pixel in those retrievals. Now, what I don't show here is that we can also have a much better handle on what the uncertainties are in our retrievals, and that can be penetrating into models for operations as well as for the climate science. We're also taking this information and the daily retrievals from the MODIS instruments on Terra and Aqua, and we can use those, the time series, and our knowledge of the geometry as well as the quality flags, which is further growing the data volumes. We can use that to then piece together from these instantaneous retrievals where we may have cloud cover that's blocking our view of the surface and the snow, as well as poor viewing geometry out at the edge of the scan. We can piece this together into a continuous record on a daily basis that the hydrologic modelers are most interested in. They don't want to have to mess with the cloud cover and the poor geometry. Okay, so the other part that I mentioned here was the impacts on albedo. And this is something we've known for a long time, but we've only started in the last few years to understand its impact on runoff hydrology and glaciology around the globe. So this is a shot from WRR in the Colorado Rockies. And I won't take you through these in the interest of time, but so this is the change in the number of days of meltout, all right? So the end of snow cover. So the end of snow cover comes much earlier related to dust concentration, and we're looking at 1 to 2 months difference in meltout date due to this increased loading of dust. So with this, and these are coming from just in situ measurements, so no remote sensing involved here, so very small data sets. But what this takes us to, this knowledge then is expanding our scope, our view into what we need to leverage. We need to leverage this out of the MODIS sensor, and it may be that we need more remote sensing, more bands to be able to look at this. So how well do we know these radiative forcings? And this is what I was alluding to. Well, we don't know it well, and we know it almost nowhere, but we're now leveraging it through the MODIS dust radiative forcing in snow algorithm, which gives us retrievals such as these in the upper Colorado River Basin. And these mountains are coated with dust that comes out of the Colorado Plateau and the Great Basin. Just for perspective on this, so this is pushing 400 watts per meter squared against irradiance of about 1,100 watts per meter squared, all right? So I come from JPL, and the way that our media team likes us to portray this is in astronomical terms. So if you were to take the clean snowpack and get it to absorb as much sunlight as this dirty snowpack is, you'd have to move that snowpack closer to the sun than Venus. So this is a powerful impact, and we're starting to understand that globally this is a big driver of melt. This is the Hindu Kush, Karakoram, and Himalaya. Large radiative forcings in those regions as well. And then we're also taking the time series of retrievals, and let me see if I can get this to operate. So we're taking the time series of the snow-covered area retrievals and shrink wrapping these and putting these into annually resolved maps of snow, permanent snow and ice. Before, there's not been a retrieval like this at all. So actually, there is not a complete glacial mapping of the globe until these products came available to us. But what it required was the complete MODIS record, right? Globally resolved, and using that full spectral database, ending up with this permanent snow and ice map. This is in the Karakoram as well. And then ultimately to these broader maps. Okay, so I want to get the final data stream here to you, and I'm expanding the data volume as we go. This is the new JPL Airborne Snow Observatory, and it's targeting snow water equivalent and snow albedo. It's based on the concepts that have come to us from the Airborne Visible Infrared Imaging Spectrometer, which should tell you that we're going to be moving to greater data volumes. The two parameters that we're really after to understand snowmelt and water resources and glaciology are snow water equivalent, just how much mass there is in the snowpack. Do we not have 15 minutes? It says 9. I think I have 5.5. Okay. And then the albedo, the reflectivity. So the way water management has been done in the past is that these water managers go out, they drive a snow core into the pack, and they weigh it. And then recently we've seen, in the last 25, 30 years, we've seen the advent of the snow pillow, which gives us automated data. Now, each of these snow pillows, the area is roughly 1/10,000th of a MODIS pixel. So a single MODIS pixel. So we have a representation issue. So the Airborne Snow Observatory is an imaging spectrometer, about 400 spectral bands across the solar reflected spectrum, and then a scanning LiDAR to get us at snow depth. These are going to be retrieved from 20,000 feet at about 1.5 to 2 meter spatial resolution. So this is an imaging spectrometer retrieval. This is in the upper Colorado River Basin, and then the colors here represent the spectrum. In this case, it's AVRIS, 224 bands, right? And this is a fairly narrow swath, but the HISPRI instrument, which is one of the NASA decadal survey missions scheduled for 2022 launch, is a global imaging spectrometer, giving us the globe with well over 200 bands for the entire terrestrial surface, and then coarser across the oceans and in the Arctic regions. So we're really seeing this big transition in snow mapping. This is just showing some of the ASO retrievals. And what we have to do with those, that's the retrieval of the ground surface, get it from the LiDAR, getting rid of the trees, but then also seeing what the tree heights are. And this is also this can also be resolved into the structure of the vegetation. Greg Asner at the Carnegie at the Carnegie Institution is flying his Airborne Observatory looking at vegetation and biochemistry. And then finally, these are our retrievals, the snow water equivalent and snow albedo. Okay, so finally to the meat of what you guys are here for, and this is the JPL Snow Data Server. And I'm going to take us into a video that Chris Mattman recorded, which really describes the standing up of this Snow Data Server. So about 2 years ago, I was a few months into being at the Jet Propulsion Laboratory, and I realized that I had not yet found the programmer that I needed, the computing team that I needed. And I woke up one morning and the first word out of my mouth was something I can't say. I guess I could, it's San Francisco, but it was an expletive. And I needed to find that right team, and I needed to do it fast because it was February. We needed to get the data up for water managers to be able to start using these data. And fortunately, we had Chris Mattman with his team with the open source emphasis. So the Snow Data Server is distributing all of the products that I've described before, as well as energy balance data across the western U.S. And all of this has been done based on open source retrievals. These are just some big data grand challenges from Chris, and in particular, Geosciences, that's me, says I've got an IDL or MATLAB algorithm that I will not change, and I need to run it on 10 years of data from the Colorado River Basin and store and disseminate the output products. So let me get you to Chris here, since he can describe it far better than I, and hopefully the volume's going to work. Uh-oh. It's not working. Does your technical crew? Are you the technical crew? Okay. What's that? Is it right here? No. It's on the Mac. It looks like it's muted. Okay, well, we won't hear from Chris, but you can see Chris. So what Chris talks about is the process of standing up the Snow data server, and in particular, the great utility of the open source, and in particular the OODT from Apache, and how readily we were able to get these data disseminated and get this robust structure available not only to the scientists that we're working with, but also to the water managers. And so I come from the physical sciences, and Chris comes from the computing sciences. It really has been an amazing transformation in the data system in that capacity. At any rate, I will leave it there since we're over time. Thank you. Okay.
Thank you. Do you want to take a question?
It's Friday afternoon.
You might want to say ODT and the word workflow.
Workflow.
The ODT is a workflow management system that you seem to like.
Yeah, well, if there is a question. Okay. All right, thank you.
Okay. The next invited talk is by Tom Jordan from the Southern California Earthquake Center.
Which one do I use?
You just click and I will advance.
Great.
And the timer does not work, but when you see 15, your timer.
Great. Okay. Well, thank you, Yolanda, for inviting me to this session. I represent the Southern California Earthquake Center, which is very involved in what we would call earthquake system science, kind of diagrammed here. We really look at seismic hazard analysis, but we have to interact with many people, from scientists to engineers to emergency managers, in trying to convey the information that we have, develop the information, convey it, so it can be used for the practical purposes of understanding earthquakes and mitigating their risk and helping communities become more resilient. One of the very important aspects of this type of science is large-scale computation, and this sort of shows you one of the basic computational pathways that we have, which is to take an earthquake rupture forecast, combine it with some ground motion model, and come up with some estimates of the intensity of shaking you might expect during an earthquake. Now, this has typically been done in a fairly empirical way, but recently, through high-performance computing, we can now do earthquake simulations well enough, that is, with enough physical resolution and many times enough to be able to use them in a physics-based approach to seismic hazard analysis. In order to understand how earthquakes work, we have to not only be able to calculate the ground motions, but we have to understand what goes on in the faulting process, and that requires running some very complex dynamic rupture models. All of these models require having a good representation of the Earth's structure in which the earthquake is occurring, and that requires us to take data, very often the earthquake data itself, and invert that data for some sort of structural representation. So these are our basic computational pathways. We implement these pathways on what we call computational platforms, and in SCEC we use that term to mean a vertically integrated system of hardware, software, and wetware that allows us to achieve some of these large calculations. And one of the implied capabilities of our computational platforms is the use of workflow management tools. And so what I'm going to do today is outline some of the use that we have found for these workflow management tools, and to also give you an idea of some of the needs that we have recognized in this work. So our computational challenges include the requirement for multiple codes with different types of system demands, the involvement of very large numbers of processes and files, and we have to be able to trace and reproduce our results. And of course, workflows are important in giving us the capability for doing all of those things. The workflow projects that we have been working on at SCEC include a platform we call the broadband platform, which allows us to calculate what I'll call small suites of earthquake simulations, that is less than, say, 100,000 or so, for specific engineering applications. We also have a platform we call Cybershape, which uses very large suites of calculations, hundreds of thousands to millions, for full-scale probabilistic seismic hazard analysis. We call that PSHA, and you'll see that a little bit later. There are new types of earthquake simulators that not only these are physical models of the earthquake rupture process that takes place within complex fault systems. And so when an earthquake happens, a fault ruptures, it can change the stress state within the system, and that changes how earthquakes will happen in the future in that system. And we have now physical models that can track very large numbers of earthquake ruptures. We can produce earthquake catalogs, simulated earthquake catalogs, with, it says 10 to the 6. Actually, it's 10 to the 6 years, and that will involve many hundreds of millions of specific earthquake ruptures. In order to be able to do the structural inverse problem, we now use techniques called full 3D waveform tomography, which are real computational hogs. And these require, again, many hundreds of thousands of simulations. And then finally, I'll mention the Collaboratory for the Study of Earthquake Predictability, where we use automated testing of operational earthquake forecasting and earthquake early warning models to evaluate those models and see how suitable they are for practical use. I'm going to really just mention the broadband platform, Cybershape, and the Terra 3D platform in this talk. I won't talk about the other two. Yolanda put up a listing of some geoscience workflow paradigms that came out of the paper that she and others authored in EOS this past year. Here are 5 of them. I don't know what happened to the 6th one. Was the 6th one in the paper? It wasn't. Okay, so I got all 5 of them. I just wanted to point out that we use, or I would say, if you look at the workflow applications that we run, you would put them in at least several of these categories. Probably the center modeling paradigm for sure, high-performance computing paradigm is very important, and the metadata-rich paradigm. I don't think we are very involved in sort of filling out the whiteboard paradigm, but some of our applications do require the or we try to deliver the calculation capability to small users. So I suppose that would be number 2, the long tail paradigm. And here's an example, the broadband platform, where we actually have a couple of different things that we do with this platform. One is we have a very large validation project where we are looking at many recorded earthquakes at many stations and comparing those with synthetic seismograms produced by this platform to see how well we can replicate ground motions. That's a center-level application, very well organized with lots of developer support. But we also, this broadband platform, part of the reason we're very serious about validating is because we expect it to become a very usable platform for engineers that want to apply simulation methods in their engineering design work. So that requires we be able to deliver these platforms essentially as software packages that people can use. That, of course, means that we have to have fairly lightweight software. Well, there are a number of workflow issues associated with the broadband platform. This shows you sort of a DAG representation of that workflow. I won't go through details other than to point out that it requires a number of calculations in representing the earthquake source, the low-frequency ground motions, the high-frequency ground motions are calculated in a little bit different way, and then, of course, we do a lot of post-processing of those results. Now, the code set that's used here is very heterogeneous. A lot of this involves what you would call workflow-unfriendly legacy code, and that limits our ability to use a lot of workflow systems with this code. Also, we have to be able to support a diversity of users through software releases. So users have to be able to easily assemble different combinations of the component calculations and execute a variety of workflows. And very often these are not what you would call sophisticated users. The CyberShake platform attempts to replace this standard empirical way of calculating intensity measures through an attenuation relationship, typically an empirical relationship, with one of these computational pathways where we have to actually extend the earthquake rupture forecast. We generate kinematic fault rupture suites that sample that forecast. We compute for each of those the wave fields that are generated by those earthquake sources. We might have to do nonlinear site corrections to account for the near surface effects. Out of that we get seismograms, and from those seismograms we can calculate intensity measures. We can calculate many other things. We can actually generate what we call seismic hazard curves, which represent the probability of exceeding some ground motion level over a particular period of time, and this of course must sample the entire rupture forecast. You might have a little earthquake near you that will cause strong ground motions or a big earthquake further away, and you have to have simulations for all of those events. And if you do that if you get hazard curves from many sites, you can produce hazard maps which represent the ground motion levels that might be exceeded in some particular period of time. So if you want to build a structure to be safe for earthquakes, you would have to make sure it could withstand shaking it might experience during its lifetime of 50 or 100 years. So this is a big revolution in seismic hazard analysis because we're effectively replacing empirical models of how the ground motion amplification works with physics-based models. There are some tricks we use to make this computationally efficient. This shows you a map of the Los Angeles region where we have done our preliminary calculations just to sort of show the size of the problem. This is for 225 sites. For each of those sites, we generate 440,000 earthquake simulations, and you can see the kind of computational cost of that and some of the large data sets that are generated. In particular, notice that there's about 190 million separate jobs that have to be run to do this particular workflow. Again, a sort of a DAG representation of some of the components of the CyberShake workflow, not dissimilar from those that you saw for the broadband platform, but there is again a significant post-processing step. This is just another representation. We've actually extended the CyberShake platform to include a high-frequency components using stochastic techniques. And again, you see the very large number of sort of repetitions you have to make of each of these calculations. And this is for a single site, and you have to do this for many sites. So the workflow issues on the CyberShake platform, one of the problems is that current workflow tools assume support for remote job submission. They assume you've got a full OS on the compute nodes, that you've got a fairly homogeneous set of cores. But if we, in the very large systems that we use, these leadership class high-performance computing systems, the big supercomputers, a lot of the new systems don't support remote job submission. They have bare-bones OSs, and of course there's GPUs, co-processors, and all kinds of fancy gear loaded up in these machines. On some of the largest, newest HPC systems, there's very limited workflow system support. And of course, this is where we really need the workflow, so we're going to have to work on this problem. I list this last point because the issue of capability versus capacity computing is important to us. And to show that, here's an example of a calculation that we are trying to do, we're setting up to do. This is to do a statewide, California statewide, CyberShake calculation, 1 hertz deterministic wave propagation up to 10 hertz stochastic. Just look at the cost there. It's of order of 400 million computer hours, and you can see some very large data sets approaching half a petabyte or so, or more than a half a petabyte, multiple petabytes for the complete data sets. The full 3D tomography workflow is even more complex. I'm going to go very fast and not talk about the details of it, but we are starting to get results we're actually deriving statewide California models. This is the work of Po Chen and others, and this will be used in the CyberShake calculation I just mentioned. We need easier methods for constructing and changing workflows. A lot of these full 3D calculations are done by individual researchers working with lots of seismic data. Again, they have to use high-performance computing resources, and we need self-contained workflow systems on these large-scale facilities. We also need to be able to support manual and interactive processing stages where an investigator has to come and kind of interrupt what's going on to assess how things are going and then go back into the workflow, and that's right now cumbersome. So a summary of SCEC workflow needs are, I would say, we really need workflow tools for large calculations on leadership class systems. We need lightweight workflow tools that can be included in the scientific software releases. We need methods to define workflows with interactive people in the loop stages, and methods to gather both scientific and computational metadata into the databases. And CyberShake is a good example of this because once you have done that gathering and have constructed the databases, you can now take a seismic hazard map and work yourself backward. You can say, well, I'm interested in a particular site, let's say San Onofre. Wonder why? That's where the nuclear reactor is. You can get out hazard curves, you can disaggregate, you can go back to the rupture models and actually get the seismograms for some type of, let's say, safety analysis. But that requires extremely well-organized, very large databases. So I will leave you with that thought. Thank you.
Questions for Tom? So I wanted to ask you, what's the difficulty of having the workflow systems installed in the high-performance facilities? What's the challenge there?
Well, some of the ones I mentioned, again, it's a lot of the fancy gear. And it's also just policies associated with these centers. For example, we use remote job submission, and they do not allow remote job submission. So that's part of the reason why you have to have self-contained workflow systems that do not require that capability. One example.
Thank you. Thank you very much, Tom. There's one last talk in the session. I apologize for ending late. It's hard to keep track of time when this timer is broken. So this is from Bila. Okay.
I'm going to use
So I think you can switch with this. You have to watch the time because you have up to 15.
Thanks for still staying for my presentation. I'm going to talk on application of the data management workflow to support the regional scale hydrologic modeling. To do this, I'm going to use IRODS, the rule-oriented data management system. Although there are several data management tools available in this for different areas. For my project or for my research, this IRODS tool is very much related. And the data challenges, data-driven scientific community are facing enormous data challenges. The data are remotely stored and located, and as well as the collaborators. And also there are several types of data available. For example, simulation data, there are observational data, experiment data, and also there are available like web data, media files. All these types of data creates a huge amount of data that's the scientific community needs to manage, and during request to manage. And to do this, logical arrangement of the data and metadata and long-term access to this data requires special attention. In the case of modeling, models are rarely automated to get access to the data and transformed into required information that are required for the models. And these models, and from these models gets when it gets large data from heterogeneous sources, this work becomes very difficult. And also reproducing the model results from for reproducing the model results for this model reproducing these models directly from the main source or main web source is very impractical, or sometimes even very difficult. So DataNet Federation Consortium DFC is initiating a project supported by NSF, where a number of cyber infrastructure partners and science engineering initiatives are brought under one umbrella to develop national data infrastructure. And these partners and initiatives are enabled to collaborative research on shared data collection by integrating the live data resources from various these partners. And they use IRODS for this purpose. And IRODS is a data management tool that can search, access, add or manage data and metadata from various sources. And this data is first stored in the IRODS data system, in the IDOS server, where IDOS metadata catalog keep the track of this data by using rule engine and microservices. So what is rules and microservices? The rules are critical and fundamental component of the IDOS system, and rules are using rules called microservices interface routine to execute a particular job. And microservices is a small, well-defined function that performs a certain job, and systems programmer and application programmer can develop these microservices and compile it into IDOS server code. Another feature is one can chain these microservices and execute a series of tasks with one into one rules with one rules. Okay. This is the architecture of the IDOS resource server, where client or admin interface interact with rule invoker. The rule invoker defines a set of rules. The users use this rule for managing or executing or do some operation of the data in the IDOS server. The rule engine executes microservices controlled by the rule, and they also manage recoverable microservices in the case of error. And if the execution is successful, then the data, then the current state of the current state information is loaded in the current information services. And also, if someone changes the rules and microservices, these changes are validated through consistency checking modules in the IDOS system. So in the data management grid, if someone in the UNC wants data for its own, then the request first is goes to the metadata catalog, from where metadata catalog provides information where the information to the UNC server that where is the data available. If the data available in the USC in Columbia, then USC in Columbia either from its own server or from a remote location collect the data and provides it to the UNC. So my objective is to automate the data processing, preparation and result visualization workflow for the VIC model, and share this reproducible workflow in the federated network to enable collaborative research on shared data collection. So the VIC model solves the water and energy balances, and typical resolution for this model ranges from 1/8 of a degree to 1 degree. And also this resolution depends on how much data we are using for our simulation. And the data we required for VIC model simulation are meteorological forcing data, topography data, and soil and vegetation data. For meteorological data, we require precipitation data from NCDC, also maximum minimum temperature from NCDC. And then we collect wind data from National Center for Environmental Prediction and National Center for Atmospheric Research program. The topography data we are collecting from Hydro 1K dataset, and soil and vegetation data we rely on the LDAS data source. So this is the typical data processing steps of for VIC model, where for each type of data one has to execute manually for certain certain steps, and these manual steps are very time consuming, and it is a potential source for human error. And also difficulty to reproduce the result of this from this process is very high. So so we want to use IROS to automate the big model simulation, and the end-to-end big IROS application we divided into 3 parts. First, we automate the data preprocessing, then we run the big model, and then we do the data post-processing. In data preprocessing, we will do automate data access, gridding, and rescaling. In the big model, we'll do big simulation, and it will happen outside the IROS grid. And once the simulation is done, we will collect the data into the IROS system and creating maps and other figures and etc. Okay, so in the data preprocessing, we will automate precipitation, maximum, minimum temperature data, and then we will combine it with the wind data to create the total meteorological data set, and we separately collect soil and vegetation data from the NCDC, from the LDAS source, and feed it to the VIG model for simulation. This slide shows how the data processing steps are converted into data processing workflows using IROS, where we will use the required steps and convert it into rules. Like for temperature rules, we will only use these steps where collecting the data to regrid the temperature data and automate this with IROS. For precipitation data, we will use all the steps and create the precipitation rule. Similarly, we will do wind and soil vegetation. And we can also add these rules together to make a weak precipitation rule, but we want to keep, we want to provide flexibility of creating this precipitation, temperature, and wind data or vegetation data separately, so that other discipline in this federated network can use this precipitation and temperature data. But if someone wants to use only weak, then weak data prep rules can execute the whole data processing with one rule. So this shows the data processing workflows where the green boxes are showing the scripts that are from VIG model, and the left to it precipitation, the column under the micro rule are the rules using IROS that executes the model scripts and it creates the output. Where, again, and this number of series of micro rules are integrated into precipitation precipitation rule, or this macro rule, which upon which execution it will collect data directly to the NCDC web data, stored it in IROS system, and successfully execute all the processes it needs to create the end product. Similarly, for post-processing, currently we are doing manually to create the results, but after returning from the conference, I will engage myself to create the rules for automating these results. And to do this, I will similarly I will create micro rules for each of these steps and integrate it into flags.r for like for soil moisture. I will create a rule for soil moisture and execute this rule to create the figures at once. Click. So conclusion from this from my work, or for our work, is to IROS can be used to automate data collection and precipitation, data collection and preparation from heterogeneous sources for hydrologic modeling. And these approaches reduce the preparation time for the data processing and reduce the potential error for while large scale hydrologic models are applied. and model simulation become shareable workflows in the federated network and allow the others to reproduce the model results. And thank you. And
any questions? Thank you for sticking with us, and I'm sorry we ended the session so late. It's very hard to keep track of time with the broken timer. So you've seen presentations here on from scientists that are using workflows, the SnowMelt OODT workflow framework, the iRods workflow framework, the SCEC project also using workflows, and you've heard about combining workflows with modeling frameworks. I think that we want to see in the future a larger spread of workflows throughout geosciences, and we're interested in your thoughts on how to do that. Thank you.